Thank you, Bent and Lena and the organizing committee for inviting me here and letting me see beautiful Copenhagen. It's a great little city. Our big city, actually. It's much bigger than where I come from. So I'm going to talk today about early math development funded by the National Institute of Child Health and Human Development in the U.S. and the National Science Foundation. Now, there we go. So I'm going to focus on, I'm going to begin with several key findings of a 4-year longitudinal study where we followed kids from preschool, so 2 years before kindergarten, so they're 3 years, 10 months or so, all the way through the end of first grade. I'm going to focus on that. Our basic goal for that particular study was to, just leave these on, was to identify the core early quantitative knowledge that predicts readiness for math learning in first grade. So what do you need to know at 3 and 4 years of age to be ready for more rigorous math learning in first grade? And our sample is a sample of kids who are at risk for learning disabilities. And so we were also focused on what might predict long-term difficulties. First, I'm going to talk about the key core areas that we focused on in the study to kind of narrow things down to figure out exactly what it is kids need to know in the early years. Since it's a longitudinal study, we have multiple assessments of quantitative skills. We have 4 assessments, as I'll show you, of these skills. And so we'll look at developmental patterns in some of these key areas and how those patterns relate to later achievement. We've just started a follow-up study to this. So we identified, I think, the core areas that are necessary for kids to know during the preschool years when they're about 4 years of age or so going forward. And so now we are now focused with this LD, Learning Disability Innovation Hub, funded by the National Institutes of Health, focused on trying to understand individual differences in this early knowledge that I'm going to show you in just a bit. So this is the basic design of the study. Let's see if that works. Nope. Anyway, so the kids, so it's 4 years. The kids received math and reading achievement assessments every year. We did Wechsler formal IQ assessment in the first year. And then we did nonverbal progressive matrices IQ assessment in year 4. We assessed executive control, attentional focus, and inhibitory control, as we heard yesterday, as being an important component of kind of the domain general component of learning difficulties. We assessed that 2 years. The quantitative tasks I'm going to show you we gave in both preschool years, and we assessed them twice in each year. So we had 4 assessments of those. The math cognition and working memory data there, I'm not going to show you too much of that, but I'll show you a little bit later. The tests that we gave in kindergarten and first grade overlapped, and in first grade were identical to tests we gave, assessments we gave in a kindergarten through 9th grade. Previously we did a 10-year longitudinal study, so we overlapped the 2 studies so we can make more precise connections between them. So our sample was recruited from Title I. That is a U.S. federal program that gives school districts additional money for students who are, for preschool students who are deemed at risk for long-term learning difficulties. So we have a good relationship with the directress at this program, And so we were able to work in the schools and do all the assessment with them. So it's a good sample in terms of the questions that we're interested in terms of long-term risk. Some of them had difficulties with attention or moved or something. So we wound up with almost 200 kids in the 4-year sample. IQ was average overall. Math achievement was average overall, although we had a lot of variability in this sample, more variability than you would typically get. It's pretty diverse there. Based on the criteria for getting into the program, it was skewed toward lower income folks, although we did have some higher income folks, kids from graduate students and stuff that parents were well educated, but they didn't have much money. And they started at 3 years and 9 months of age, so fairly young. So our task was, there is a very large literature on infant number cognition and recognition, recognizing dots, the relative quantity of dots. There's a pretty good literature on, actually very good literature on, 1 and 2-year-olds and 3-year-olds on counting knowledge and all sorts of quantitative types of things. And that tends to be a field kind of in and of itself. So we know a lot about, infancy, early preschool, number competency stuff. And then you jump to school-related mathematics. And there's a whole huge literature on that. So we know a lot about kindergarten and development going forward. But there wasn't any bridges between those two literatures. And so because the researchers who worked in these two areas didn't communicate much, better now. So there was no way to bridge those two literatures. And so our goal with this particular study, or one of the goals, was to look at all of the early tasks and skills that the early folks look at and assess a wide range of them, follow these kids up through first grade, so see when they're ready to do well in math, and try to build this bridge and to narrow things down to only the core set of things that kids really need to know during the preschool years. There is preschool curriculum in the U.S. for Title I kids, but it's extremely broad and so not very deep in any one particular area. So we wanted to put some focus in that. I'm not going to go over all 12 quantitative tasks because a lot of them, turns out, aren't that important. But there are a few tasks that really did come out to be pretty important. Numeral identification, so we'd show them an Arabic numeral, 1 to 15, and just see if they could identify it. This is a 1, this is a 5, this is a 12, or whatever it was. We did a numeral comparison task, so if they knew 7 numerals, we kept those 7 numerals, shuffled them up, and showed them pairs of a 3 and a 7, which is more, 7 in this case, so I got that one right. And so we did that. We have 6 trials on that. Verbal counting is just, how high can you count? 1, 2, 3, 4, 5, then go. If they got to 100, we had them to stop. The mean was actually just 12. So they just knew a few number words, not that much. So they're, an at-risk sample, so it'd be a little bit lower than we would expect. And enumeration, we had 20 objects, and we wanted to see if they could count them and point and get the pointing and the number words aligned and get it correct. So a little bit more complicated than verbal counting, the ability to apply your counting knowledge and your verbal number word knowledge to an actual counting task and an actual enumeration task. And one thing that came up is extremely important, as you'll see, is cardinal knowledge. And so this is knowing the exact quantities represented by number word. So you have the number word for. Do they understand that that word represents a collection of 4 objects of any type? So that they know that. Seems very simple to us, and it is to us. But actually, developmentally, it's a very complicated task. Acquiring this knowledge, actually, the basics of it extend about 2 years during the preschool years, and continues to get elaborated over the next several years. So kids basically learn 1 initially, and I think there's huge variation in this in the literature where people have studied this in kids. The samples tend to be upper middle class, from upper middle class families. And so that I've suggested to them that, well, maybe that biases things a bit. Nah, it's good. We're good. Well, it does. So I think the literature on this probably overestimates the learning and how easy it is for kids. But in any case, so kids learn 1. They learn that 1 represents 1 thing. And they can pick that up with language. 1 cat, 2 cats, 1 ball, 2 balls. And so the language, singular and plural, gives them some hints on that. So they pick up 1. And when you get beyond 1, it's just random. They don't know. It's a quantity or whatever. To go from 1 to 2 takes about 6 months. And these are with these fairly privileged kids. It takes about 6 months for them to add 2 to their list of cardinality knowledge. And then another 6 months to 3. And then another 6 months to 4. So we're really spread out. It is not an easy skill for these kids to learn. Once they get to about 4 or so, they have a conceptual insight that each additional word in their counting string, at least in what they know of the counting string, is 1 more than the number before it. And that's called the cardinal principle knowers. And so once they hit 4 or so, then they get 5, and then they get 6 pretty easily, and then they're called cardinal principle knowers. So they have this concept that there's a 1 increase with each successive number word. They don't really get the insight that, it applies to all number words until they're probably in kindergarten or more, but at least for the number words they know, they do have this conceptual insight. So those are the key tasks of the 12 that we're looking at. And even among those, only a couple are really important. So cardinal knowledge is really kids' first conceptual understanding of formal mathematics. We also assessed the approximate number system, the dot task thing we saw yesterday, and that is thought to be an evolved and intuitive sense of relative quantity, but it's just approximate. There's more stuff here and less stuff here, but doesn't have the precision of formal mathematics. But a lot of people thought the approximate number system was an important part of the foundation, as we heard, of mathematics development. And so we had a couple of measures of the approximate number system in our study. And in fact, it is correlated with math achievement, as other people have found. But what we found was, once we put cardinal knowledge as a predictor of standardized math achievement, say at the end of the first year of preschool or at the second year of preschool, the approximate number system was no longer important. So any relation between the approximate number system and math achievement was mediated by cardinal knowledge. So maybe it helps kids pick up what these number words mean early on, but once they get them, the symbolic system seems to just take over and be critical. So we did that in one analysis. Elizabeth Spelke told me she came and visited my university. We had dinner and stuff, and said, "Oh, I don't believe these results," because she does some approximate number system stuff. I said, "Okay, it's fine." So we did it again, and we added to the sample and stuff, and we found the same thing. Once we finished all of the kids through the first 2 years of preschool, so we had end of preschool standardized mathematics achievement test, the TEMA. We wanted to know, okay, can we take all of the measures we gave when they started preschool and see what comes out as predictors of end of preschool achievement. So how ready are they for kindergarten? I'll just skip over these. We did a bunch of preliminary things, Bayesian, some fancy stats, trying to narrow down the number of predictors because we gave a lot of measures here just to reduce the risk of misidentifying or getting false positives. The important thing here is the cardinal principle knower here. So we looked at, contrasted 6 knowers, so kids that were cardinal principle knowers at the beginning of preschool. So they started school already in really good shape. And then we contrasted them with 1 knowers, 2 knowers, 3 knowers, and 4 knowers at the beginning of preschool. So how are the differences there? And it's predicting mathematics achievement, almost 2 years later. All right, so the outcome measure is standardized math achievement at the end of preschool. And here, we had a lot more predictors, but the preliminary analyses we did kind of pared those down to most critical ones. The Bayesian stuff is a little better than standard stats in terms of reducing false positives and stuff. So we did that there. The highlighted p-values are the things that are significant in predicting end of preschool math achievement. And so letter recognition, nonverbal IQ in preschool. But the critical knowledge is right here. So these contrasts here, so kids who started as cardinal principle knowers, relative, when we compare them with 1 knowers, we see that there is a negative 0.75 value. That means that the 1 knowers are 0.575 standard deviations below the cardinal principle knowers by the end of preschool, which is quite a large effect. And the effect was a little bit smaller for 2 knowers and not significant for 3 or 4 knowers. Now we have 2 things here. One of them has letter recognition and the other has numeral recognition. We ran those separately because they were so highly correlated. So kids who knew their alphabet, we had an alphabet measure too, also could identify their numerals. So whatever their parents are helping them with letters, they're also probably helping with numerals. We did them separately. But even when we control numeral knowledge, we still get these big deficits. So kids who are only 1 or 2 knowers at the beginning of preschool are going to start behind, fairly substantially at the end of preschool, controlling IQ and parental education. Actually, that gap gets bigger as we move forward, as I'll show you. So once we completed all of the assessments through the end of first grade, question came up, does the age at which you become a cardinal principle knower make a difference? So we tested them at the beginning of preschool, as I said, the second semester of the first year, the beginning of the second year, and the spring semester of the second year. So we had 4 assessments of these kids. The basic belief at that time in the field was that, well, as long as you're cardinal principle knower by the beginning of kindergarten, you're okay. You don't have anything to worry about. And you know what happens when you make assumptions? Things go bad. And so we had 141 of the 197 completed almost all of the assessments through first grade, so we just focused on those where we had a lot of the data. And we gave a variety of tasks based on things that had come out as being potentially important predictors of achievement at various times. We also added in the ANS task, which is discrete quantity discrimination. That's just the dot task we saw yesterday. We just included it in there for theoretical reasons. The important thing is the red ones that give a number. So those are the different ages at which kids were given this task. And we wanted to know, you know, were they cardinal principle knowers? They get 5 or 6 on our task. You know, at 3 years, 10 months, or at 5 years, 2 months. And about 10% of the sample never got it, even through the end of preschool. The number processing stuff here in first grade overlapped our 10-year kindergarten to 9th grade study. So we gave number processing, how quickly can you associate a set of 3 and a set of 2 with the numeral 5, so accessing quantities associated with symbols, and basically speed and accuracy of that. Addition strategy task, you know, how do you solve 8 and 3? Do you count on your fingers, 8, 9, and 10? Or do you remember the fact, or do you do a variety of other strategies? So we looked at the sophistication of the strategies they use to solve those problems. And we had a number line task, a 0 to 100. How accurate were they? All of those tasks load on a single factor, which we called number system knowledge. In our previous study, we had the exact same measure, number system knowledge, beginning of first grade. And then we gave employment-relevant math competency tests used by labor economists to them when they were adolescents. So it's like, okay, are they ready for the labor market if they're just going to go to work, for example? And we found that the NSK predicts performance on these measures 6, 7 years later, even when we control for standardized math achievement, IQ, parental background, and a variety of other things. In fact, the number system knowledge task is actually more sensitive to individual differences in math development than is standardized math achievement tests. So again, we did all the basic stats. So we looked at age of becoming a cardinal principle knower, contrasted with kids who did not achieve it by the end of preschool. So our contrast group was they never got it, and then what's the difference between those who never got it, those who knew it at the beginning, second assessment, third assessment, fourth assessment. We use the ANS task, object comparison, which is kind of another ANS type task, verbal counting, numeral recognition, same task I showed you earlier. We use start of preschool scores, and then the difference between where they started and where they ended, so their gains in those basic skills as predictors of number system knowledge at the beginning of first grade. It's important to control domain general abilities here, and again, we did extensive assessments of those. We got executive functions, first, second year preschool IQ, verbal and nonverbal IQ, included letter knowledge, and then we had kindergarten IQ as potential predictors as well. Okay, and then we cut those down using these other stats to make sure we didn't have false positives. Then we added end of preschool math achievement as an additional control, and then everything in there to try to get rid of the effects that I'm going to show you. So I'll walk you through this. These first 3, these rows here include only the measures that survived our Bayesian and initial analyses that were identified as the core predictors of number system knowledge in first grade. So nonverbal IQ, numeral recognition, and gains in numeral recognition. Okay, so those are important. Knowing numerals is important. The really key finding is that those who were cardinal principle knowers at the beginning of kindergarten or picked it up before or at the beginning of preschool or picked it up by the end of the first year had about a 1 standard deviation advantage on number system knowledge in the beginning of first grade, which is a huge effect. The advantage early on was about half a standard deviation, end of the first year, end of preschool, and now, beginning of first grade, their advantage is double that standard deviation. So I said, well, maybe it's just confounded with general math achievement. So we added standardized mathematics achievement at the end of preschool in there as a control. And as you can see, the effects were a little bit smaller, but still quite large. And we thought, well, let's just throw everything in there, parental education levels, letter recognition, verbal and nonverbal IQ, which was the first year of preschool, 2 years of executive functions, and then the kindergarten IQ test, threw everything in there. The numeral stuff was no longer so significant, but you can see that we still have very large, almost standard deviation gaps there, or advantages. So getting and becoming a cardinal principle knower, they started at 3 years, 10 months. So getting it around the time they're about 4 years of age really was a big predictor of readiness for learning mathematics at the beginning of high school, controlling all of the usual subjects there that might be potential confounds. Now, it could be, well, maybe the cardinal principle task is just picking up something like general attunement to academic types of skills, or just picking up general academic achievement rather than a domain-specific math achievement there. And so we did the same analyses to predict word reading skills, word reading fluency, which we did at the end of kindergarten. And as we'll, oops, well, I'll just walk over here. As we'll see here, none of these effects are significant, and they're all pretty small. So knowing being an early cardinal principle knower has no effect on later word reading skills. So it's a very specific effect. Then we looked at numerical operations. This was standardized math achievement at the end of kindergarten, and we're getting some similar effects, but a little bit weaker than we found with the number system knowledge task. Remember, the number system knowledge task is more sensitive to individual differences in early number skills and critical math skills than a standardized math achievement test. So kids who are cardinal principle knowers by about 4 years of age, plus or minus a few months, before or early in the first year of preschool, have a 1 standard deviation advantage in number system knowledge in first grade, which for kids, well, for anybody is a huge effect, but for kids starting a standard deviation behind is a huge deficit, huge something to catch up with. Then we controlled IQ, prior math achievement, executive functions, parental background, and other factors, and didn't have much effect on that. So it's it's actually a very robust finding. It's unrelated to later reading achievement, demonstrating discriminant validity, that it's not just picking up general academic skills. was related to later math achievement, but less strongly than the number system knowledge, which we argue is, we've shown is better predictor of later quantitative outcomes. So the implication is that children's understanding of symbolic mathematics accelerates after becoming a cardinal principle knower. Now remember, their advantage went from half a standard deviation to a full standard deviation. So the gaps are growing from the beginning of preschool to the beginning of the first year of formal schooling. So if that's true, we did a follow-up study, and we examined the relation between age at which they became a cardinal principle knower and numeral comparison task. Now, the numeral comparison task gets at some of the same issues we heard about yesterday, about understanding relative quantity based on number symbols. Speed of making numerical comparisons, you just show them a 3 and a 5. Which one is more? 5, how quickly and accurately they are at making these sorts of things, is actually a pretty good predictor of math achievement, and a better predictor than ANS, approximate number system acuity. Numeral comparison, we argued, is kind of the early stage of learning the relations among numbers. So the number system knowledge is really not only access to what these symbols represent, like a 20 or 2 or 10 or whatever, but also the relations between them. So a 10 is the same as 9 and 1, and 7 and 3, 5 and 5, and so forth. So you can decompose it into equivalent sets that represent the same quantities, and the numeral comparison is beginning to get at the development of those things. And that's what we think why these early cardinal principle knowers had this long-term advantage. So kids were randomly presented for this numeral comparison task. As I said, numbers from 1 to 15, took the ones they recognized, and then they got 6 trials of, a 1 and a 3, which is more. And so we just looked at number correct on those. And we added the ANS task, the dot task, in there just as a comparison there. And we excluded the kids who never became, and didn't even know 1 by the end of preschool. But anyway, so the black one in A is numeral comparison performance of the kids who are cardinal principle knowers at the beginning of preschool. The red line is the kids who got it in the second assessment. The blue line is the third assessment, and the green line is the fourth assessment. So that's number comparison knowledge % correct. The dashed line, dashed horizontal line there is what percentage you'd need to get correct for it to be statistically significantly above chance. Okay, so they look different. It looks like these kids are all kind of at different levels. But then what we did was align them. The 0 is the assessment where they became cardinal principle knowers. And so if they became cardinal principle knowers at the beginning of 2nd grade, which was the third assessment, so that would be 0 for them. The second assessment would be -1. The first assessment would be -2, and the end of the preschool assessment would be 1 for them. And incredibly, once we aligned all of these kids up based on when they became cardinal principle knowers, their number comparison performance is basically the same, suggesting that really they're not understanding relations among numerals until they have this conceptual insight that these numerals represent quantities in a very systematic, successive way. So very, very cool results there. And we see all of the performance, all the kids were above chance on the ANS task, consistent with it's an intuitive, evolved sense of quantity. When we line them up, all the lines come together, and the slope does actually increase a bit, consistent with what we heard yesterday about having conceptual knowledge, kind of refining the approximate number system. But the rate of change in the approximate number system is slower than the rate of change in the symbolic, numeral comparison task. So we thought, well, that's probably why these kids who are early cardinal principle knowers have this one standard deviation advantage at the beginning of first grade, is because you can't start developing this system of knowledge among numerals until you actually know what each individual numeral represents, a number word or Arabic numeral. Makes perfect sense. And so I think that showed that. And basically what that means is comparing to kids who aren't cardinal principle knowers at the end of the second year of preschool versus those who are cardinal principle knowers at the beginning of preschool, basically have 2 years of informal learning occurring. They're beginning to develop this network of number knowledge or numerosity or whatever because they had this insight earlier. The kids that were delayed can't really start building this network of knowledge until they've hit this conceptual insight. So as we heard yesterday, consistent with once you have the symbolic stuff, it does affect performance on ANS tasks, and so the ANS gets more integrated into the symbolic system rather than the ANS being the foundation for the symbolic system. All right, so we had an at-risk sample here, as I mentioned. I can ask, what happens to kids who are high risk of math learning disability? Kind of how does their profile look over the years? We defined at-risk as below the 25th percentile on the standard math achievement tests in the preschool years. We gave at the end of first grade again, end of second grade. And if a kid performs low on a math achievement test 1 year, it says, well, follow up and see what happens next year. That in and of itself is not necessarily an issue to worry about. We've done a number of studies that. So if you have a poor performance 1 year, but you bounce back the next year, those kids that have kind of up and down performance, cognitively they're fine. But the kids who have low performance 2 years in a row or more, of course, those are the kids you need to worry about. So we wanted to say they had to be below the 25th percentile in both years to be considered at risk. And then we got a band of typically achieving kids that were kind of right in the middle at both preschool assessments and at the end of first grade. And we found something we didn't actually expect. There was 37 kids out of our sample who had low standardized math achievement scores at both preschool assessments. But then when we looked at them in first grade, some of them continued to score poorly, and some of them had average scores. They kind of bounced back. So those that continue to consistently perform poorly, we call math learning disabilities. We'll see the percentile there, they're at or below the 10th percentile in all three assessments. So they're consistently having difficulties. The kids who we call recovered were at the 10th and 12th percentile in the first and second year respectively on the math achievement test. So they were pretty low, but now they're average at the end of first grade. And then the average kids were average all the way through by definition. And so we did a number of a very extensive Felicia Chu, my graduate student there, did a very extensive analysis trying to discriminate kind of what is the difference between these long-term disabled kids and the kids who kind of bounce back over time. And a couple things came out. One of those was executive functions, so the ability to control attention and inhibit kind of irrelevant things. Both the learning disabled and the recovered kids performed poorly, relatively poorly, on that relative to the average kids in the first year. But what's interesting is the recovered kids had normal executive functions in the second year. So they showed a lot of gain from one year to the next. Did a number of other tests to make sure that it wasn't a regression to the mean sort of thing for them, and it wasn't. So other tests did not show the same rate of change as the executive function one. So they did something, I don't know what happened to them, but they had strong growth in executive functions between the first and the second year of preschool. Recovered student, substantial gains in EF. We looked at a number of other factors. This is a given number. This is the cardinal knowledge ones, task. The green guys are the typically achieving, the yellow are the recovered, and the red are the learning disabled. We'll see at time one, both the recovered and the learning disabled kids aren't doing very well in this task. Time two, it's not much difference. By the second year of preschool, the kids who recovered are really starting to get that. Whether that was due to the changes in executive functions, I don't know. Maybe it was. The group differences were less, were smaller for some of these other verbal countings, contrast tasks, or the ANS tasks that didn't make too much difference. So there's some interesting things going on there with these two groups. Okay, the kids who were recovered, even though they're average on the standardized math achievement test, they still had subtle deficits on the number system knowledge measures. They were behind the typical kids in memorizing addition facts, so consistent with an arithmetic fluency, potential arithmetic fluency, associative learning deficit, but a fairly subtle one, but it was there in our data. So they didn't remember as many facts. They're also slower at identifying the quantities represented by Arabic numerals, like a 5 or so. They could do it, but they were slower. So there were some subtle number-related deficits in these kids, even though they do okay on a standardized math achievement test, which isn't going to be as sensitive. So, oops, there we go. Got it out of order there. So we found some interesting things in this first 4-year study. And our argument is that cardinal knowledge is really the linchpin to early math development. And that the age of acquiring this knowledge is critical. So this is the gateway, we think, into symbolic learning of mathematics and preparation for learning formal mathematics at school entry. Not only is it the gateway, the gate has to open early. Delayed opening leads to deficits, as I said, deficits at the beginning of first grade. Okay, now the question is, since the age of acquisition is so important, we want to know, why do we have so much variability? We had some kids who knew it when we, 3 years and 10 months, they were already cardinal principle knowers. Then we had other kids who didn't get it even after 2 years of preschool. So there's a huge variation, even though they're all a Title I sample. So the question now is, in part of our new project, the Learning Disability Hub, is to figure out why we get this variation, identify the factors that are correlated with early versus later cardinal principle knowledge, and then hopefully that will provide the groundwork for the development of focused interventions for these kids. And as a lot of you know, a lot of interventions fade out. You know, you work with a kid and blah, 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 they get better, but 2 years later, there's no difference between them and kids that didn't get it. You find that in a lot of areas. In some areas, if you have a multi-systemic intervention, you're intervening in the schools with the kid, maybe in the peer group, depending on what it is, and maybe also in the home, then you get less fade out. So if you hit kind of multiple aspects of, you know, their functioning around whatever it is you're interested in, then that might stick better. And that was kind of our argument here. So we want to look at, we're focused on cardinal number knowledge and supporting number competencies like enumeration. We have child-based assessments, home-based assessments. We'll have 3 visits to the home over the 2 years of preschool. In that, doing a variety of things that I'll explain here in a bit. And we're going directly in the classrooms as well. So it's quite a large sample, quite a large project. Hoping to get 150 kids. We're probably about 85 now. We got one more cohort to assess to start next year. So we're kind of, you know, in the first third or so of this project. And that's all we're doing with these kids. So we have, at the top there are things that the kids are getting that are domain-specific, math-related type of things. All of the things that we found were important. In our previous study, we added cardinal knowledge for numerals, Arabic numerals, in addition to number words. Spontaneous focus on number, which I think you were going to hear about later, but I guess not today, which we didn't assess the first time, but we think might be important. And a variety of other things. We added math vocabulary and number line to the task. Again, we're controlling for domain general stuff, so we'll get executive function measures, letter identification, so early pre-literacy. They get standard IQ measures. We added additional working memory measures and stuff, so we'll get a pretty good assessment of their general domain general skills, standardized math achievement in both years. We're going into the classrooms for each of the kids, and they're being observed twice a year each semester, so we'll get 4 assessments on them. And we're looking at things like on-task behavior, compliance with the teacher, stuff like that, because attentive behaviors in the classroom for older kids predict achievement, controlling all of, you know, domain general and a variety of other things. We're looking at what the classroom teacher is actually doing during the class, number-related stuff, and then we're also getting teacher reports on child in-class attention, hyperactivity, and what they say they're teaching. The parents are getting quite a bit of assessment as well, a lot of attitude stuff, mathing, anxiety, math attitudes for themselves and for their kids. We're assessing their verbal, nonverbal, general abilities. We're giving actual math and reading achievement tests, standardized reading achievement tests to them. Prior studies have looked at home variables, but just have the parents report, you know, how much you like math, how good at you are, stuff like that. So we're actually measuring their actual standardized achievement. Demographics. We're doing the home assessment, which is a standardized structure of the environment assessment for, you know, the learning environment and the social environment for the parents. We're doing that. And we developed a child-parent number talk task, doing a birthday party together, videotaping that. We're transcoding, you know, getting all of the transcripts, you know, the dialogue from it and transcoding it, and we'll look at the number words they use, whether they focus on cardinality, whether they're counting, and exactly what they're doing. So the task is designed to elicit number talk And we're doing that twice for them. And we're starting to get results, a huge variation among parents. Some parents hardly use numbers at all, even in this task that tends to elicit numbers, and others are very, very sophisticated in how they're talking to their kids about numbers. So we have quite a bit of work to do. Kind of just put that up there. So basic model, want to look at complex number development. So that would be cardinal knowledge performance on the give-in test, the number word task. We'll have an Arabic numeral cardinality task as well, and then the number comparison sort of thing. So the performance on these three tasks should really give us a pretty good idea of how good the kids are at each of the four assessments. And we just kind of made some predictions. We think a number of things will contribute to that. Complex number exposure at home, maybe parent attitudes, parent beliefs, and so forth. One thing that's come out with our preliminary analyses of first sample was that math anxiety is related to kids. The parents' math anxiety is related to the kids' cardinal number knowledge at the beginning of preschool. So we're thinking that, well, maybe the math anxious kids have less sophisticated number talk with their kids. And we're still coding the number talk task. It's kind of complicated. So we haven't looked at that yet. But that's the sort of things we'll look at. Then we have math language, that's math vocabulary, so forth. So we need to integrate all of these home measures with the classroom measures and the child-centered measures into kind of a mix of things that is predicting complex number development and potential interactions. So developmental interactions, let me just go to the next slide and that explains it more. So for example, we'll look at things like complex, this would be like a structural equation model. So complex number would be a latent task identified by those variables up there. Complex exposure to number at home, that could be the parent's math achievement, parent-child talk, or whatever it is. We'll figure out once we get more data what is going on there. And what could be potentially interesting is if parents change the complexity of their talk, their number talk with their kids based on how much the kids know. So it could be, for example, that kids who know a lot in the second year, complex number talk, have parents who from year 1 to year 2 increased or became more sophisticated in how they talk to their kids. In other words, these would be child evocative effects. Do parents differ in their sensitivity to the quantitative knowledge of their kids? And if they are sensitive, do the parents then increase the complexity of their number talk? And so we'll look at those types of child effects controlling prior year effects once we get the second year data. And there's a whole bunch of other things we hope to do as well, but that's just some kind of where we're headed and what we're thinking in terms of planned analyses. So, right on time. In conclusion, we do have an inherent evolved sensitivity to relative quantity, identified as the approximate number system. Lots of species have that. Nothing special there about people. Big push in the literature was, okay, this is the foundation for symbolic mathematics. A lot of work on that. We looked for it very hard, actually, and it's just not there. And so it's important. It is correlated with math achievement, but doesn't seem to be the foundation that some people think it is, at least from our data. Rather, kids' understanding of cardinality, early understanding, seems to be really the key to it. And even though it seems easy to us, kind of second nature, so to speak. As I said, there's a long developmental period for that, at least 2 years. These for upper middle class kids. It's probably longer for at-risk kids. Long period, so it's something that's not easy to learn. And it is, in fact, unique to humans. Chimpanzees can learn to learn that 3, the numeral 3 is greater than the numeral 2, and 4 is greater than 5, but they have to learn each and every number by rote, and often with thousands of trials. They never have the conceptual insight that, well, 7 is got to be 1 more than 6. They have to be trained on 7 and trained on discrimination of those. So the conceptual insight is uniquely human. And it is kids' first mathematical induction, their first conceptual understanding of symbolic mathematics and number. And it continues to be elaborated for years. Of course, we have number theorists who that's what they do. They continue to study patterns in number. So learning the value of individual words, and we assume numerals, which we've added to this new study, is a first step in learning the relations among number system symbols and number system knowledge. And as I mentioned, this number system knowledge predicts long-term economically relevant outcomes, even controlling standardized math achievement. So it is more sensitive to individual variations than standard achievement tests. Critical finding, I think, is that individual differences at the beginning of preschool are related to their trajectory of number learning, and that in turn influences readiness to learn formal symbolic mathematics at the beginning of first grade. As I said, the factors that contribute to this, we got 2 years of variation among kids in terms of developmental timing of these. We have no idea what is contributing to that variation. No doubt it has to be something in the homes that's contributing to it, and we'll find that out with this new project. But there may be child-centered effects, there may be in-class attention behavioral effects as well, and we'll look at all of those in combination. So our goal over the next few years, it'll take us probably about 3 more years to finish this project, is to identify these factors and kind of prioritize those in terms of what is important. And then these would be targets for multi-systemic interventions. So I could imagine that an intervention with these kids would involve the parents, the home environment, structured things for the parent and the kid to do together, more structured activities for the teachers, maybe behavior management for the kids who are a little attention challenged and so forth. But we'll see. I think that's it.
Thank you very much. A lot of information, and you have to know it will be taped, so afterwards you can sit at home and listen and look for it afterwards. I think it would be a nice way of doing it. But still, there could be questions, so now you have the possibility to ask David for something. And we have the students around. He will see Christian is on his way.
Looking at the graphs that you referred to, a few of your findings, the lines that...
Okay. See if I can find that one. Right here?
Now it works. Okay. So looking at the graphs that you referred to as being cool, those, yeah. Mm-hmm. It seems like a simpler solution than interventions, and the multi-systemic approach seems like these students just need to start school later on. it seems like they're just a year or two later in their development, so why not just start their formal math education a year or two later? It seems like the speed at which they're developing.
Right. Well, yeah, that's the speed at which they're developing once they became cardinal principle knowers. But if they start, but what's important is basically before they hit that point, they're not really learning anything else, conceptually about mathematics. They can learn to count and stuff, but they don't really know what it means. And if we started them later you mean start them first grade, start them in third grade or whatever. But that would put them on a path where I think they would perform even worse on these economically relevant tasks. So it would just keep them behind unless we gave them 2 additional years at the end of, okay. Yeah, so I guess that's approach. I think a less expensive and easier approach is to figure out what is driving that variation early on and try to address it when they're 3 and 4 years old to get them on track and get them ready for the system that's already in place.
I just have a clarification question.
Mm-hmm.
Your LD hub intervention, are the children 2 or 3 years old, or are they 4 and 5 years old?
Sorry, I should have mentioned that. They're the exact same Title I schools as we used in our first study. So the
4 or 5 years old.
Yeah, so they'll start about 3 years, 10 months, 3 years, 9 months, I think our first cohort was, and then they'll go for 2 years of preschool, and they're in Title I, just like our sample here.
Shouldn't you make the intervention earlier?
Well, right, yeah, we don't have interventions yet because we don't know how to intervene.
Okay.
So what we want to do is figure out, okay, what is going on in the home? There's a lot of things going on in the home. There's a lot of things going on in the classrooms. And we know that whatever's going on in the home and the classroom is not enough for a lot of these kids. And so we want to know, okay, we want a focused intervention. What is it that is going to speed up their conceptual understanding of number symbols specifically? And it could be parent-child number talk, the sophistication of that. It could be parents' math anxiety needs to be addressed. And it could be a lot of other things there that aren't important. So we want to figure out what's not really important and what really is important. And then the interventions, when they're designed, would be focused only on those key important components of whatever it is.
Thank you so much for explaining your research. I was just wondering in a practical aspect, and you may not have the answer yet, but I know there's some preschool teachers in the room. I know there are a lot of people studying early education. And in the Nordic countries, most preschools are play-based. Usually up until 6 or 7, 6 often. And many parents in the rooms or people that work with parents, I was just wondering, do you have any tools that people could start using right away to help children develop the cardinal knowledge?
Yeah, good question. We don't have any formal tools right now or set procedures, which is, I think, what ultimately will be needed, kind of a script, kind of what you need to say. From what we're getting from the parent-child number talk task and the kids' performance is probably the complexity of the number talk with kids. A lot of parents do routine stuff, 1, 2, 3, 4, 5, so you learn, the counting string and how to enumerate things, but they're not talking about sets of objects. So we have 3 things here and 2 things here. So the more, that is a level of sophistication that we're not actually seeing in a lot of the parents. And I think that explicit kind of separating out and and either explicitly or implicitly identifying the cardinal value of collections of objects, I think is going to be really important. And having parents who are dealing with their kids with numbers greater than 10. So a lot of parents are focused on 2, 3, 4, 5 or so, and it's good, kids need to learn those types of things. But parents that are talking about larger numbers, the teen values, 10, 1, 10, 2, or maybe 11 or 12, in English, their kids seem to be doing as well. So I think there's a lot, I think we're going to get a lot of traction around the parent-child discussions of number and especially the cardinality discussions. But we don't have a set kind of, this is a set of things that we can design for you to do right now. But that's my hunch based on what prior work has said and what we're seeing in our data.
Thank you.
Mm-hmm.
Other question yet, Karen?
Thank you. Yeah, thank you, David.
Thank you.
I think it was a very rich presentation you gave us, and all the other workshops done are also very rich.
Mm-hmm.
There are so many things that we could come to think about, and how can it be combined, and how to use it in practice. That is something that really needs very hard thinking, because we can't say that because this turns out to be better in the long run, then it is exactly that we should do. But it's an important knowledge to have and think from. And also an information, maybe Ingemar knows more about it, but in the Nordic countries, the biggest longitudinal studies we have are from Norway, and it's made in Stavanger by Elin Reikås. And it could be also very interesting to deep into. And she has data from toddlers to 19 years old. So that is also a very rich. No, you don't. No. Okay. No, but that's also a kind of study that it is almost impossible for us in the Nordic countries to do. So we are looking very much into what you are doing in the States with more money than we have.
I was just wondering, do you factor in, because you factor so many things in, but do you factor in language? Because you said that earlier that one is a low income area, or like a group of local income, but is it also like multicultural families, or are they only English speaking? Because
no, we have a very diverse. Our sample here was pretty diverse. Our current sample is even more diverse. So we have a lot of Spanish speaking folks. We also have people from the Middle East and elsewhere. So we're getting translators
because I'm
to help
thinking
with
language might also factor in.
Right. Yeah. So we'll look at that. We might have enough Spanish speakers to contrast with the English speakers, but in any case, we will have some type of control for that. But I don't know if we'll have a big enough sample to look at multiple languages there. But we'll see. We'll see once we get all the data.
Yes, I have a question. You said you are going to use the test for spontaneous focus on number from Minna Hanola.
That's right.
But the Finns made an invention program for those kids with poor spontaneous focus on number. Which it's called Nallematte in Swedish, but some sort of bear mathematics using the gold lock and the three bears as a sort of. But it's tasks doing in kindergarten early preschool in where they try to address those kids with poor spontaneous focus on number, and I think they had they published results from that.
Okay. Yeah, I'll look that up. Yeah. So if we find that, well, we have the spontaneous focus on number in our study, because we think it's potentially important, and if it comes up as important, then that intervention could be part of this multi-systemic type of thing. So yeah, there's a number of things we expect we'll have to do with the kids directly, with the parents, and in the classrooms. Thank you.
Thank you very much for your presentation. The last part of it reminds me of some research which is going on in Denmark, inspired from UK, and that is in science, about establishing a concept of science capital. Mm-hmm. Have you thought of establishing a concept of math capital?
Math capital. Oh, okay. Yeah. So in terms of a general human capital sort of thing, having this knowledge is in building it up. Yeah, that's a good idea. I think that's exactly what that is, and what the number system knowledge is getting at. It's capital. It's a foundation that they can build on.
The capital is referring to Bourdieu. He started working on social capital.
Okay. Thank you.
Thank you very much. I think we will give a hand for David. Thank you for coming.